everyone, welcome back to Fractal Frontier Maths. In the previous video, we discussed the Picard-Lindelof theorem, a fundamental result that guarantees existence and uniqueness of solutions when the function f of xy satisfies the Lipschitz condition with respect to variable phi. If you haven't watched that video yet, I strongly recommend it. The link is in the description below. It will help you clearly understand how today's example connects with that theory. In this video, we are going to study an important question from the CSIR NET Mathematics June 2013 paper. This problem perfectly demonstrates what happens when the Lipschitz condition fails. That is, the existence remains but uniqueness is lost. Let's begin by recalling Peano's existence theorem, which lies at the heart of this concept. Peano's existence theorem states that if the function f of xy is continuous in a neighborhood around the point x0, y0, then the initial value problem dy over dx equal to f of xy subject to the initial condition yx0 equal to y0 has at least one solution in some interval around x0. The theorem does not guarantee uniqueness, it only ensures that a solution exists. To guarantee uniqueness, we need a stronger condition, which is the Lipschitz continuity as given by the Picard-Lindelof theorem. Here f of xy is x y raised to the power 1 by 3. So here f of xy equal to x y raised to the power 1 by 3, which is continuous function around x0 y0. Therefore, by Peano theorem, the initial value problem dy upon dx equal to x y raised to the power 1 by 3 subject to the condition y0 equal to 0 has at least one solution. Okay. Now we will check if the function f of xy satisfies the Lipschitz continuity or not. So for this, we will calculate the derivative of f with respect to the variable phi, which is 1 by 3 x y raised to the power minus 2 by 3. Okay, is not bounded in the neighborhood of 0, 0. Therefore, the function f of y equal to x y raised to the power 1 by 3 is not Lipschitz continuous function with respect to variable y. Okay, so now we will analyze the options. The first option, the function does not satisfy a Lipschitz condition with respect to y in any neighborhood of y equal to 0, which is a correct option. The second option is there exists a unique solution for the initial value problem. Since we have that f of xy does not satisfy a Lipschitz condition with respect to the variable y, so we cannot say that the given initial value problem has a unique solution or not, but it indeed has at least one solution. So option number 3 is not correct. The given initial value problem is dy over dx equal to x y raised to the power 1 by 3 subject to the condition y0 equal to 0. So we will use separation of variable method to solve the initial value problem. By separating the variable x and y, we get dy over y raised to the power 1 by 3 equal to x dx. On integration, we get y raised to the power 2 by 3 upon 2 by 3 equal to x square by 2 plus an integration constant a. Since y0 equal to 0, we will get the constant as 0. Therefore, the solution of the initial value problem is y raised to the power 2 by 3 equal to x square upon 3. Also yx equal to 0, that is the trivial solution, is also solution of the given initial value problem. So we have two solutions. One solution is y raised to the power 2 by 3 equal to x square upon 3, and other solution is yx equal to 0. So the option 2, there exists a unique solution, is not correct, but there exists more than one solution for the initial value problem is correct option. Hence option 1 and 4 are the correct option for the given problem. That for any alpha greater than equal to 0, yx defined by this, that is for mod x less than equal to alpha, we define yx as 0, and for mod x greater than alpha, we define yx equal to plus minus x square minus e square divided by 3 raised to the power 3 by 2 is also a solution to the given initial value problem. So we can say that for each alpha there exists a solution, therefore the given initial value problem has infinitely many solutions. So in summary, if fxy is continuous, then the initial value problem has at least one solution, that is the continuity of fxy guarantees the existence of the given initial value problem. If we add one more condition, that is fxy is Lipschitz continuous with respect to variable y, then the initial value problem has a unique solution, that is continuity plus Lipschitz continuity with respect to variable y guarantees the existence and uniqueness of the given initial value problem. This theorem is, the first one is called Peano's theorem and second one is called Picard-Lindelof's theorem. So the present example shows that existence without uniqueness. That is, if you found this explanation helpful, like, share and subscribe to Fractal Frontier Math. Check out the previous video on the Picard-Lindelof theorem, whose link is in the description box. See you in the next video.